Welcome back to Calculus 2. This is section 2.2, volumes by slicing. We're going to look at the slicing method and various applications of the slicing method. To begin, let's recall that we know the formula for the area of a rectangle. This rectangle has length L and width W, and we know a formula for computing the area enclosed by the rectangle, length times width. If we add in another dimension, height, then we know a formula for computing volume of this box, length times width times height. Note that length times width, that product is what we were looking at the previous slide, area of a rectangle. That would be the area of the top of the box or the area of the bottom of the box. But equally, if we were to slice the box in a manner parallel to the top and bottom, that we would recover a copy of this rectangle with measurements L and W. We'll call this the cross-section area occurring at some arbitrary height between 0 and h. So now, rephrasing this volume formula as area times height, you want to think that if I were to take a cross-section of the box at any height between 0 and h, what would I produce? I'd produce a copy of the top or bottom, and I know how to compute that area, length times width. That is essentially the slicing method. The difference is that here, our area is constant across all cross sections. In the case of, for example, this pyramid, if we were to take cross sections horizontal to the base, that the cross sections would have varying area. Let's dive into this. Suppose that we take a cross section at height I, or the ith slice of these n cross sections. And note that if you were to change the slice that you pick, that the area of that slice would change. Nice? So pick one. And then the area of that cross section, this is a nice square. It's easy to compute the area of this square. Term that a sub I. Good. And then for this slice that we've picked, the ith slice, if you were to move from this ith slice to the I plus first slice, that you would move some distance delta h. So if you were to multiply a sub I times delta h, we would produce a volume measurement. Call that v sub I. And then this v sub I is approximating the volume found at this height at the ith slice. Okay. So for each slice, we can compute a v sub I given by the area of that slice and then multiply by delta h to move to the next slice. And then summing up all of these VIs, we get an approximation to the volume of the pyramid. Nice. Now all we need to do is take a limit. What are we taking the limit in? The number of slices. Let's go ahead and do that. Taking the limit in the number of slices, we recover the true volume of this solid. Beautiful. Let's see how the book works this example. So we've repositioned the pyramid so that slices parallel to the base are perpendicular to the x-axis. And then we can simplify this picture in the picture on the right by just taking a cross-section vertically of the pyramid. And then what we want to think about is at any depth into the pyramid, depth x, what is going to be the area of the cross-section? Here we're representing the cross-section here on the left to have sides measuring s, so that if we can come up with this measurement s, we can get the area of that cross-section by squaring s, the area of a square. Good. And then that area of the cross-section is occurring at x. Here we've positioned the vertex of the pyramid to occur at the origin. And then we want to consider x is all the way from 0 out to some value h. Very good. So in this simplified picture, what we're interested in is coming up with s as a function of x. But if you notice, we have a small isosceles triangle, which is similar to a large isosceles triangle. So we can use similar triangles and come up with base s of the small isosceles triangle over base a of the large isosceles triangle will equal height x from the small isosceles triangle over h. As we're interested in coming up with an area function given by s squared, we want to solve the equation for s. Simply multiply both sides by a. Looking good. A is a constant, h is a constant. So s will vary linearly with x. The whole point was to express out s as a function of x in order to be able to write down a of x. So we take this expression for s and square it. And then at each location x occurring between 0 and h, we want to take area as integrand in this definite integral from 0 to h, and doing so will compute the volume of the pyramid. Excellent. So here's an opportunity for you to pause and verify. Put all those pieces together and verify that the area of that, the volume of that pyramid is 1/3 a squared h. And after you've verified that, take a moment to adjust your computations to find that the volume of a circular cone is 1/3 pi r squared times h. So instead of a pyramid, change your solid to a circular cone. In the volume integral computation, for a of x, you're going to use volumes of circles rather than squares. Nice. Let's do another example. So, we've considered solids described in a single familiar word, pyramid, cone. Now, let's find other methods to describe a solid. So imagine, if you will, some type of solid, and place that solid on your desk. And suppose that the base of the solid is nice and flat. So it's sitting there and it's creating a footprint on your desk. Okay, let's describe the region that the solid and your desk interface in. Suppose that that solid has a base given by y equal x squared and y equal 9. So these two curves, one is a parabola opening up, the other horizontal line, are going to intersect and define a region. Let's take a look at that picture. Parabola opening up, x squared, vertex at the origin, nice symmetry with the y-axis, y equal 9, another even curve. Intersecting, where are they intersecting? When is x squared equal to 9 at positive 3 and negative 3. All right, so we can easily compute the area of this base, but we're interested in computing volumes. And then this is just the base of the solid, which is sitting on your desk. Now what we want to do is we want to consider slicing into the solid. Well, how do we want to make our slices? We want to take our slices so that as we slice perpendicular to the x-axis. Let's take a look at that. So here is one such slice made perpendicular to the x-axis. And we're going to allow that slice to vary from negative 3 out to positive 3. Good. Now, we can easily compute the length of this line segment. Take the large y value 9 and subtract away this small y value, x squared. All right, well, we have to come back and think, well, how are we getting volume out of this? And what we want is this 9 minus x squared line segment to be the hypotenuse of a right isosceles triangle. So here's a right isosceles triangle. Hypotenuse is measuring 9 minus x squared. And for any x between negative 3 and positive 3, we want to consider the area at that x of this right isosceles triangle. Add up all those areas, in other words, integrate, to produce the volume of this solid. Okay, so our job right now is to come up with the integrand a of x. Well, we're in a good situation because we're given a right triangle. Thus, we can use the Pythagorean theorem. We know the measure of the hypotenuse. We can introduce a new variable, s, which can be expressed out as a function of the hypotenuse, thanks to the Pythagorean theorem. Because this is an isosceles triangle, the two sides will measure the same. Thus, a of x will be 1/2 s squared. All right, let's quote the Pythagorean theorem. The sum of the sides squared is equal to the hypotenuse squared. We need to come up with an expression for s squared. Here we have two copies of s squared. So put them together, then divide through by 2. This expression on the right is s squared. Take the expression on the right, multiply by 1/2, and come up with a of x. Fantastic. Let's put this all together. Take our area function, a of x. This area, where does it occur? It occurs for x's between -3 and 3. Dividing by 4, let's pull that out as 1/4. And then expand out the binomial squared for a simple form of an integrand. Evaluate. Antiderivative. Plug in the bounds. Come up with the value. Fantastic. So this is a volume where we describe the base, and then to that base, let's make slices, and then use that information to come up with the integrand and compute away. Here's an opportunity for you to have some fun. And a very similar notion. You have a base, sketch out the base, and this time the slices perpendicular to the x-axis are now semicircles. So that's half of a circle, and you know the formula for computing areas of circles. Beautiful. Next is a challenge problem. Use the slicing method to determine the volume of a tetrahedron with a base side of 4 units. The main challenge is to force yourself to think clearly. Keep it simple. Now, in this problem, you'll find that you'll use a fair bit of trigonometry, the Pythagorean theorem, similar triangles. And a hint is to integrate with respect to height. Next, we're going to look at an application of the slicing method to solids which are formed by revolving a curve about an axis, solids of revolution. So here we have a blue outer shell and then a red circle, where that circle is a cross section of the blue outer shell taken perpendicular to the axis of rotation of the outer shell. That outer shell is a revolution of the reciprocal curve y = 1/x for some x value, say x = 1 to x = 2, about the x-axis. What's happening here is that that outer shell is rolling back up onto itself and then exposing the original curve y = 1/x. The red circle is helping visualize any given point on the curve y = 1/x. Pick a point on the curve y = 1/x. That's going to have a distance to the x-axis. Let that be the radius of this red circle. Then for that point, pick a point on y equal 1 over x. It has a distance to the x-axis. Then take that as the radius of this red circle, so that this point revolved about the x-axis would trace out the red circle. Then if you were to take all of the red circles and add them all up, put them all together, that would produce this outer blue shell. What we're interested in is the area contained, the volume contained within the blue outer shell. Good. So let's look at nice pictures given by the book. We'll come back to the 1 over x in a moment. First, let's do this example. Let's take this parabola, f of x being x squared minus 4x plus 5. Let's shade a portion underneath this curve from 1 up to 4, and then revolve this region about the x-axis and compute the volume. So here's another picture, a picture of the solid produced by revolving the blue shaded region about the x-axis, and we want to compute the volume of this solid. So our bounds of integration will be 1 to 4, and if we pick an x anywhere between 1 to 4, we'll get a height given by the function f, which will be the radius of a cross-section of this solid. Now, that cross-section is going to have area, a of x. That cross-section is going to be a circle. You know that the area of a circle is given by pi r squared, but that radius, r, is given by the value f of x. We go from the x-axis up to the curve. How high is that? That's f of x, so that's the radius. In this case, the function f is a nice parabola, quadratic x squared minus 4x plus 5. That's our radius function, which we know we have to quantity square. Thinking back to the picture, our bounds of integration were 1 to 4. Plugging this into the volume integral, which has definite integral, bounds of integration, and integrand a of x, we copy down a of x. To get ready to integrate, we'll need to open up this trinomial squared. This is a trinomial, we're squaring it. X squared doubles up to x to the 4th. X squared can produce an x cubed term by matching up with negative 4x. That can occur twice. X squared terms occur with 5 matching up with x squared, but also x squared matching up with 5, giving you 10. But then also negative 4 quantity squared. 10 plus 16 gives you 26, and so forth. Good. Now we have a simple integrand for which we can find an antiderivative and evaluate. Excellent. Do another example. This is solids of revolution. Find the volume of the solid generated by revolving the region bounded by the x-axis, y equal 1 over x equal 1, x equal 2 about the x-axis. Okay, so this guy, y equal 1 over x, that's going to give the radius. And this is the nice picture we were looking at earlier. This is in fact called Gabriel's horn. And this red circle is going to have a radius 1 over x. What are the bounds of integration going to be? 1 to 2. Radius 1 over x. Radius quantity squared times pi. This is the area function of the cross-section. Where are we taking cross-sections? From 1 to 2. 1 over x, that's x to the negative 1, quantity squared, x to the negative 2. Integrates up to negative 1 over x. Plugging in, we come up with pi over 2 cubic units. Fantastic. Your turn. Basically the same problem, but instead of using the reciprocal function, try using the root function, y equals x, radical x. Good. So this was solids of revolution. We have a curve, defines a region with the x-axis, and revolve that about the x-axis. Well, that's exactly what the disk method is all about. The disk method is a formalization of computing volume for solids of revolution. And it's a wonderful opportunity to explore how to formally write this down. So what's required? Well, we want to have a function f that's continuous. Remember, continuous functions are integrable functions. Non-negative, this is a little bit of housekeeping, bookkeeping. Keep things clean and nice. Let the region defined by f occur above the x-axis rather than below. And then how can we describe that region R? We want the region R to be bounded above by f, below by the x-axis, to the left by x equal a, and to the right by x equals b. A nice well-defined region R. Good. And then we want to take that region R and we want to revolve it about the x-axis. Then the volume of that solid of revolution, disk method and solid of revolution, same notion, is given by this volume equals the constant pi out in front. It's my preference. Definite integral, bounds of integration, a to b. Integrand, r squared. Little r squared, radius squared. Where do we get the radius? F of x. So that's the disk method, which is exactly the same thing as computing volume of solids of revolution. All right, one more topic. Let's do a little play on the disk method called the washer method. So here's the formal statement. Let's do a little picture and then we'll come back and read over this formal definition. So let's start with a cylinder, but let's hollow out the center of the cylinder. And then let's consider, well, what volume is remaining? Well, in a very simplistic way, the computation of the remaining volume can be computed by taking big minus small. What's big? Big is the original volume before the cylinder was hollowed out. What's small? Small is the amount that we hollowed out. How much did we extract? Take that difference, and that's the volume that remains. We know that these two formulas, V big and V small, can be computed out as integrals. We can write them down as formulas, but if we write them down as integrals, then we can allow for the original solid to not only be a cylinder, but something where the radius continuously varies. And the amount that we extracted can also have a continuously varying radius if we assume that it is a solid of revolution itself. And then looking at V big minus V small, we have a difference of integrals, which in the formal statement of the washer method is nicely combined, thanks to properties of integrals, as a single integral. And then looking at this single integral, the integrand is a difference of the large radius squared minus the small radius squared. Breaking it up into V big minus V small will help us to not make a mistake in placement of the power 2. We won't do big R minus little r quantity squared, but we'll do big radius squared minus small radius squared. Okay, let's do an example. Nice. We have a region defined in the xy plane, bounded above by y equal x, bounded below by 1 over x. And then the region R occurs for x's falling between 1 and 2. Because we know that we're going to revolve region capital R about the x-axis, then the large radius is going to be given by x, and the small radius will be given by 1 over x. Let's write this down as large radius produces a large volume, and the small radius produces a small volume. Now, using the reciprocal to give a radius for x's coming from 1 to 2, we computed that earlier. That portion of Gabriel's horn computes out to a volume of pi over 2. And then the linear y equal x, let's see what radius x produces as a volume. So x squared goes up to x cubed over 3. There's a pi out in front. Evaluate that at the bounds. 8 minus 1 is 7, so we get 7 pi over 3. We'll take the big volume and subtract the small volume to get 11 pi over 6. And this is an example employing the washer method. Now it's your turn. Here what we're going to do is we're going to do some prep work and get ready to integrate with respect to y. So we've already done this region capital R revolved about the x-axis. Let's do prep work to revolve region R about the y-axis. So the bounding curves here on the left are given in terms of y equals a function of x. And here in the picture on the right, you want to look at the bounding curves as x given as a function of y. Good. And then having the bounding curves written out as x is a function of y, you can revolve the region R, which here has been broken up into an R1 and an R2, since we now want to consider integration with respect to y. We're going to take cross sections which are perpendicular to the y-axis. And when you get those horizontal line segments, you'll notice that you enter the region and exit the region on different curves depending on whether you're intersecting with R1 or R2. Very nice. Otherwise, it's exactly the same. You want to do big minus small. A very simple notion. Fantastic. That is the end of section 2.1, volumes by slicing. Thank you so much for watching. See you on the next one.